is not an insulated tool either. Now, it is this plastic and this rubber is an insulator, but it's not an actual rated insulated tool. An actual rated insulated tool is going to have yellow or orange or yellow and red handles. There's going to be a very pronounced finger shroud here to prevent you from gripping on the metal part of the tool. It's going to keep your hands back away. On a screwdriver or a nut driver like this, the whole shaft will be covered in that dielectric material, and they're 3 to 5 times more expensive than a standard pair of pliers. Like this Klein Journeyman Series, not Journeyman Series, but the Series 2000 steel, hardened steel cutting blade tool. This is like a $50 lineman's pliers. It's about $150 on the insulated version. The insulated tools are really expensive, and if you buy any, you're going to find they come in like a little padded case. It's because they don't want to nick up the insulation and rattling around in the toolbox. So if you're going to get insulated tools, protect them and use them when you have to. Everything else you can bang around and use this as a hammer. You don't use your insulated tools as hammers.
Do you use that stuff at Home Depot? Is that more like...
More like electrical supply house or specialty tool suppliers. Of course, everything is available on Amazon right now.
There's a very small amount of things you can get there insulated from like Home Depot and Lowe's, but it's not really as well, not really a big market on it there.
Yeah, they're really, you know, working with linemen's, working on power lines are going to use them. Industry is going to use them.
Yeah, what I'm hearing, you can steal them out of the back of a lineman's truck.
Huh? I did not advise you to steal anything.
Eric told us to hit the electric trucks, so we're gonna hit them.
Take the copyright people. Get away.
So now we're going to get into some of the nuts and bolts and how we work with this. Electricity has 4 aspects. In fact, electricity comes in 4s for some reason. You cannot see electricity. You cannot tell by looking at something whether it is energized or not. You cannot tell by looking at it whether it has, how much voltage it has on it. You can't tell anything about it by looking at it. Electricity is invisible, and that's what our instruments are for. The instruments are to us what a cane is to a blind person. A blind person uses their cane to navigate their environment and identify what is close to them and where things physically are in space. But since we can't use electricity, we're going to use our instruments to quote-unquote see electricity, but we're not actually seeing it. We're looking at the effect that it has on something else. So you need to really get good at using your multimeters. We're going to start practicing on that today. For a diagnostic technician working on any kind of machine of any type, electricity is what makes that thing do what it does. Can you think of a single thing that you service that doesn't have some part of electricity working on it? There's nothing. How many of you are saying, oh yeah, I got a fireplace. Don't have no electricity. Yeah, actually it does. It generates electricity at the pilot flame. There's electricity there. Not much. You measure with the meter. You can see it. Everything has electricity. Oh yeah? What about my water heater? Yeah.
Millivolts.
Millivolts. The new water heaters with the Icon, the Bradford White Defender water heaters, or any other water heater now, it's got that Honeywell Icon gas
I
valve.
believe every water heater is required to have
They're all
some
going
sort
there
of
now.
pilot shutoff that's going to have some sort of electricity.
They're all going that way now. The Icon now is actually powered by 750 millivolts off the power pile. You ever wonder why, if you ever seen one of those, you turn it on, and it starts blinking a light? Plug it into the wall, what happens? There is electricity there. So the 4 aspects of AC electricity, of course we're dealing with AC. Don't worry about DC. Number 1 is voltage. Number 2 is phase. Number 3 is frequency. Number 4 is current. Are any of you saying, hey, what about resistance? Now that I mentioned it, do any of you say, hey, yeah, what about resistance? Thank you. Resistance is not an aspect of electricity. Resistance is an aspect of a thing. I have the property of resistance. Electricity does not have the property of resistance. An electric motor has the property of resistance. The electricity itself does not. So we need to distinguish between the property of electrical devices and the properties of electricity itself. We're going to deal with the properties of electricity first. So, voltage, number force that causes electrons to flow. It is also known as electromotive force. Voltage is also known as potential. Has anybody ever heard the phrase voltage potential? Or heard voltage referred to as a potential? None?
Somewhat,
It's a potential. Voltage represents the potential for electrons to flow. It doesn't necessarily mean that because there's voltage there, there's actually movement of electrical power or electrical power consumption. Units of measure for voltage is volts AC. We can think of voltage like the pressure inside of a water pipe. Now, if I have this water faucet, we happen to have one right here. We do this little test. Right here, we've got a pressure gauge attached to this hose bit on the outside of the house. And we are measuring a pressure of 95 psi from the meter. Is there any water flowing right here, right now, in this picture? No. What are we measuring here? We're measuring pressure. That is representing the potential for water to flow. But it's not actually flowing, is it?
No.
Now that we know that the potential for water to flow is 95 psi, we have a pretty good idea what will happen if we remove the gauge and open the faucet and just let the water flow, right? Water's going to flow pretty readily, won't it? Sure it will. If we close the faucet, what has happened to the pressure behind the faucet? Did it go up higher, did it go down lower, or did it drop to zero?
Stays the same until you relieve the pressure.
It's going to stay the same. That's right. There's no water flowing, but the pressure is there. The potential is there, right? That's what voltage is like. Voltage is similar to pressure in that it represents the potential for electricity to move. The higher the voltage, the more easily electricity will flow, or the greater the potential for electricity to flow. Now, to further the analogy a little bit more, if I just crack the faucet a little bit, I don't open it all the way, I just get just a little bit coming out. What's the water pressure behind that faucet? Does it change at all? No. No, it's going to stay the same, isn't it? What about the amount of flow? Is the amount of flow high or low?
Flow is low.
Flow is low, because I just got a little dribble coming out. The amount of voltage present does not necessarily dictate the amount of actual electricity that's flowing, similar in the way that the amount of water pressure present does not necessarily dictate the amount of water that's actually flowing. What's the standard water pressure delivered to the fixtures in a house in your neighborhood? 80 pounds inside a house. Okay, 80 pounds. Well, I tell you what, there's no quicker way to start a fight than to ask people what the proper pressure inside a house is supposed to be. I don't argue, whatever it is. So we got 80 pounds in the house. You go to the kitchen sink and turn on the faucet. 80 pounds of pressure getting supplied to that faucet, 80 pounds of pressure getting supplied to all the faucets. You open one of them, and how much water is going to come out of that faucet? What's the determining factor of how much water is going to come out of that faucet under those conditions?
How far you open the faucet?
You open it up all the way. Are fixtures rated in gallons per minute? That's the determining factor, isn't it? At this given pressure, open it up all the way, it's going to flow this many GPM. Right? So if I am opening one faucet at the end of the whole system, and I'm running, say, 2 GPM out of the kitchen faucet, because there's never enough in the kitchen sink. If I'm running 2 GPM out of the faucet, how many GPM are running through the water main coming into the house? 2 GPM. Pressure is 80 pounds in the whole system. Got that in your mind? Open up the bathroom faucet in the tub. How much does a tub faucet generally flow?
4 to 5.
4 or 5. We'll call it 5, because I like that number better than 4. 4 plus 2, or 5 plus 2 is 7. 2 GPM here, 5 GPM there. How many GPMs over there? 7. What's the pressure throughout the whole system? 80. Is the pressure determining the GPM, or is it some other factor?
The end use, the faucet.
Yeah, it's the end use, the terminal device. That's the determining factor. Open up all the faucets in the house. Are we still going to have 80 PSI in all the fixtures?
No.
Why not?
It's been distributed throughout the entire system. It's being
Reduce
used.
all potential.
What? Wait a minute. Now we have a design problem. Because we should have pipe big enough to serve all the fixtures at the same time. We should have a PRV big enough to flow the GPM requirements at the pressure requirements of the whole system. We should. I read a story recently, somebody built a stadium out east somewhere. They built this new stadium, and it was in one of the plumbing trade magazines, and the plumbing, it was like crane toilets or something, was all through the whole thing. And they did this test once they commissioned the building. They had somebody at every single urinal and toilet in the entire facility. There's like several hundred of them in this stadium, and they flushed them all at once to verify the integrity of their design. Measuring the pressure in the system, measuring the performance of the piping and plumbing systems and the drain systems. And it worked. Now, if you guys have done any plumbing work and you're like, yeah, you open up all the faucets, you're going to have a pressure loss. You're not supposed to. That's a problem. That's a design problem. Well, guess what? The same thing happens in electricity. You ever been in a home, or anywhere, when the air conditioning unit comes on, the lights dim for a second. You notice that? That's the exact same thing that's happening in the plumbing system when you're running one faucet and then somebody flushes the toilet or turns on the tub and the flow in your faucet dips a little bit. The size of the power lines coming into that electrical system aren't physically big enough to provide that uninterrupted flow. That doesn't. Did you notice that doesn't seem to happen in places like schools, hospitals, and other institutional buildings like the library? You don't see the lights dim when the air conditioning comes on, do you? Because those electrical supply systems are engineered to do it. Except for the difference between commercial and residential work. So now that when you're starting to see this, you're starting to appreciate more the nature of a finite quantity of electricity. Determined by the supply circuits that you're getting. The size of the wires coming into the house is like the size of the pipe bringing the water into the house. It has a finite ability to deliver energy. The pipe has a finite ability to deliver water before it starts to experience a pressure drop. When you start to think about voltage like water pressure in a system, it's very similar. If I'm measuring voltage at one condition, and then that voltage drops when something else happens, that's an indication of the sizing of the wires isn't big enough to handle the amount of flow that we're trying to demand at this moment. Voltage only represents the potential for current to flow. It doesn't necessarily represent the actual flow. Just like the pressure of the pipe represents the potential to flow, but it depends on how many faucets you turn on, or how far open you open the valve, how much water is actually going to move. Here's another example with voltage. Say, for example, we go to a factory building. It's got a lot of power coming in. Have you ever noticed around factory buildings in like old cities like Chicago, Milwaukee, these big industrial areas, if you've ever seen pictures from there, if you've ever been there, if you've ever been to the old parts of town, you notice there is massive electrical infrastructure around there. Huge power poles, massive cables and wire all over the place that you just don't see in residential neighborhoods. It's because they need that quantity of power. Take that stadium into consideration. How big do you suppose is the water main feeding that building? It's a lot bigger than that, right? Yeah.
Kind of pressure than usual.
Oh boy, I'll tell you what. I had the benefit one day of going to there's a water pressure regulating station in Cascade, Colorado. Cascade is called Cascade because the water from the reservoir on Pikes Peak literally cascades down the side of the mountain to feed Colorado Springs through Cascade. There's a little building in there, and the water that's coming from the reservoir goes through this building, and that is about a 58-inch pipe.